So to recap, we had an axiom, x equals x. Then we had this axiom, if x equals y, then a proposition with a replaced by x holds if and only if the same proposition with a replaced by y holds. And then we have a theorem, x equals y implies y equals x. Now, these axioms are serving to make the equality symbol work the way it should work. So these axioms are, you can think of them almost like a definition. It's not technically a definition, but they're almost like a definition for the equality symbol. They grant the equality symbol its mechanics. They grant it its meaning, almost. So what would you say to someone who disagreed with you about axiom 1, who said, I don't want that axiom in my system. I don't choose to agree to that premise. Well, there's nothing wrong with that person. You would just tell them, well, yeah, that's fine. You just must be using the equality symbol to mean something else. You're imagining something different when you write the equality symbol compared to what I'm imagining. But there's something, if you think of it that way, then there's something kind of funny about x equals y implies y equals x being a theorem. Remember, theorem means it was deduced from the axioms. But, isn't the fact that x equals y implies y equals x, isn't that just as fundamental to the meaning of equality as x equals x? Why should x equals x be an axiom, while x equals y implies y equals x is a theorem? Why should this one be deduced and this one be just accepted as an axiom? Why not just make all of them axioms? Why not just be like, this is an axiom too? This is also an axiom. It's part of what is meant by equality. If you disagree with this, then you must be using the equality symbol in a different way. Why not do that? I mean, for one thing, if we did that, it would certainly save us a lot of work, because then we wouldn't have to prove it, right? If we just say it's an axiom, we don't have to write a proof. In fact, why don't we just go ahead and do all of mathematics that way? Instead of ever writing down any theorems, we just say axiom in front of everything. And then we never have to write down any proofs, and all of our work is done. Okay, so that's definitely not a very fun game to play, right? If there are no proofs, and you just say whatever you want and call it an axiom. But there's a good reason for not, for trying to have as few axioms as we possibly can manage to have. If something can be proven, if something can be deduced from previous axioms and previous theorems, then we should deduce it. We should not make it an axiom. So, don't you think it was interesting? The one we looked at was not symmetry, it was transitivity. It was this one, that if x equals y and y equals z, then x equals z. Don't you think it's very interesting that this can be deduced from the previous things? That we don't have to declare this as part of the fundamental meaning of equality or anything like that. It actually, we have no choice but to accept this if we accept the first two. If we accept, actually, even if we just accept the second one, I think this only relied on axiom 2 here. So if we just accept this, then we have no choice but to accept transitivity for equality. That's really interesting to know that we couldn't have done things any other way. Compare this to someone who just goes through and then labels everything an axiom. It's not so interesting, right? Everything's arbitrary. They can just label whatever they want to be an axiom. Another way to think about it also is consistency. If you just go through and make whatever statement you want, whatever assertion you want, and then just call them all axioms, then how do you know you're not creating a system in which a contradiction is provable? For example, here's something you would probably never do. You'd never create a system like this. But this is an extreme example just to demonstrate. What if you made x equals x an axiom, and then you made x not equals x an axiom? Then a contradiction is actually provable in this system. And we have seen what kind of disaster that can cause. We have seen that if you prove a contradiction, then you can deduce any proposition. So as soon as a contradiction is proven, in a system where these two are axioms, as soon as you prove a contradiction, next step, theorem, x equals x and x not equal x, then everything becomes a theorem. Everything becomes provable. So you have made everything both true and false, because you've made the negation of everything also true. So that just breaks everything. The game is no longer interesting to play if everything's true, right? What's interesting is to have some things be true while some things are not true. So from the standpoint of consistency, from the standpoint of wanting to have confidence that the axioms that we have laid out do not lead to the possibility of proving a contradiction, from that point of view, we would like to have as few axioms as possible. The more axioms you have, the more likely it becomes that maybe in some way that you're not immediately seeing, the system is inconsistent and it's possible to prove a contradiction. So you want to make that as unlikely as possible. And finally, another way to think about it is I like to think of mathematics as sort of a giant argument. Like you're arguing with someone, and mathematics is this one huge argument. An argument has premises, like a starting point where you and the person you're arguing with have to agree on the premises. And then an argument also has deductions, right? The axioms are the premises of mathematics, and then the theorems are the things that you deduce from there. Now, when you're making an argument, like if you want to convince someone of your political view or whatever, then you want to have as few premises as possible, right? You want to force your opponent, your debate opponent, to agree with as few hypotheticals at the beginning as possible in order to make your argument as strong and convincing as possible. So the fewer premises you have for your argument, the more likely it is that your opponent will agree with you, right? The more premises you have, the more likely it is that there's some premise that your opponent's not going to like, and then that jeopardizes the effectiveness of the entire argument. So it's the same in mathematics. The more axioms you have, the fewer people it will satisfy, because some people will just be unhappy with certain axioms, and this does actually happen.